So in the last video segment, we were discussing linkage, how you would know if there is linkage. One way would be you tried to do a dihybrid cross and you got an F2 ratio that was not 9:3:1. And so typically you would take that dihybrid individual then and test cross them to a completely recessive individual. And when we talk about the linkage test cross, that's always going to be the setup. One of the individuals will be heterozygous for both genes, and one individual will be completely recessive. So you see that on the diagram that's here. So in part A, you have the case if the genes are completely linked. Now, this is a theoretical concept. If they were so closely linked to each other that there could be no crossing over between them, then what you would see in the gametes from the dihybrid individual would be half of their gametes would have a certain combination of alleles, in this case big M and big D, and the other half of their gametes would have little m and little d. And we're saying if there was no crossing over, then you couldn't have the other two types. If those were fertilized by a gamete from the completely recessive parent, then what you would expect is offspring, half of which are dihybrid themselves, so big M, big D, little d, and half of them would be completely recessive. That would be the offspring ratio, 1:1. But complete linkage is really just a theoretical concept. Like I said before, most of the time you're going to have some crossing over, and I'll draw it here. You can see you would get some small amount anyway of gametes that are big M with little d and little m with big D. So in this case, you would have a few offspring of the other types. All right. Now, this is compared to what's over here is if the genes are unlinked. So this is what Mendel would have, if he had done this test cross, this is what he would have gotten, because all the genes that he dealt with were unlinked. If M and D were not on the same chromosome, that's what they're saying here, then you would expect to get equal amounts of all four gamete types. And when that would be fertilized by the gamete type from the completely recessive individual, you would expect to get equal amounts of all four offspring groups. So that's called the 1:1:1:1 ratio. Okay. In reality, when genes are linked, you will get something more similar to what we're seeing in part A, but it won't be completely big M, big D, little d, and little m, little d. There will be smaller amounts of the other two types of offspring. So you will see all four groups of offspring, but they won't be in equal amounts. So that's the big difference here compared to what you would see if they were unlinked. So as I was mentioning, when you have a tetrad, if the genes cross over between, if the chromosomes cross over between where the two genes are, then you'll get allele combinations that are called non-parental. They can be called crossover, or they can be called recombinant. I tend to call them crossover chromosomes, and I tend to call the other allele combinations, the ones that match exactly what was in the original parent, the parentals. So the parental allele combinations are the ones that don't have a crossover, they're not the result of a crossover, and then the crossover allele combinations are the ones that do result from a crossover. So we go back to this cross, a more realistic image of what this cross would probably look like. Since we don't have complete linkage, we have linkage in which most of the gametes will be the parental types. And what I mean is this and this, those are the parental types. And then only a small number of the gametes would be the crossover types. So big M on the same chromosome as little d is a crossover type, and little m on the same chromosome as big D would be a crossover type. So there's a lot of the gametes that would be in the non-crossover, because when two genes are close together on a chromosome, you can get crossovers in other places on the chromosome, but not right between those two genes. So that's what we're saying. You only very rarely do you get a crossover right between where those two genes are, but you will get a small group of those, and so those are the crossover allele combination gametes. And then all of those gametes will be potentially fertilized by a gamete from the completely recessive parent. So the rule is, for any two linked genes, many more meioses will occur without any crossing over directly between the two genes, compared to the amount of meioses that do have crossing over between the two genes. So only a few of the crossover gametes will be in the pool of gametes. So the rule is parental allele combinations are much more common in the pool of gametes. And because of that, you will see significantly more offspring that result from fertilization of those parental gametes, and fewer offspring from the crossover gametes. And so when you have a dihybrid that you've crossed to a completely recessive individual, you will get all four categories of offspring. In this case, normal tall, mottled dwarf, normal dwarf, and mottled tall. But two of the groups will be much more common, and two of the groups will be much less common. And you'll be able to see it in the data. So the two very common groups are the ones that got parental chromosomes. And the two less common groups got crossover chromosomes. I'm only focusing, though, on this chromosome here. I'm not focusing on the chromosome that came from the completely recessive parent, because that's the same every time. So I'm saying the chromosome that came from the dihybrid parent is going to be either a parental allele combination or a recombinant or crossover combination, right? So the parental allele combinations will be the most common in the offspring. And that's because the parental gametes, like we said on the last slide, are much more common. So the rule is, for linkage, for any pair of linked genes, in the last example, gene M and gene D would be a pair of linked genes. The parental gametes, or we could say the gametes with parental allele combinations, will always be more common, more numerous than the recombinant gametes, or the gametes with crossover allele combinations, right? So we're going to look at the way that a simple test cross experiment would be done, and how we would calculate then an estimated distance between two genes. And you should always know, when we're using data to calculate something, it's going to give us an estimate, but we believe it's a good estimate of the distance between the two genes. So let's say you set up a cross between two fruit flies, Drosophila melanogaster, and let's say that the mother is heterozygous for two genes, body color and eye color. So that's going to be our double heterozygous individual. The father in this cross will be the homozygous recessive for both genes. And that was the rule. One of the parents has to be double heterozygous, and the other one has to be completely recessive. And so let's say we have reason to believe that these two genes, the gene for body color and the gene for eye color, are linked. So we're going to set up this test cross and see if they are linked, and if they are linked, what's the distance between the genes. So in flies, the nomenclature is typically done like this. Let's say you have, we're going to say body color. Let's say there's two alleles for body color, gray body and yellow body. And let's say gray body is the dominant and it's the wild type. So they typically put a plus for the dominant, for the wild type. And let's say yellow body is going to be recessive. So it's just going to be a Y by itself. So you just kind of accept that that's the nomenclature we're going to use. You can use any letters you want, but this is the way I'm setting up this problem. For red eyes, we're going to put a W with a plus. And for white eyes, we're going to put just a W. Okay, so let's say that's how we're going to name the alleles. And so we have a gene for body color and a gene for eye color. And then the mother, remember, she's a double heterozygote. And let's say her chromosomes are set up like this. The Y plus allele and the W plus allele are on one chromosome. And then on her other chromosome of that same type, there's the Y and the W. So that's her homologous pair. The mother's genotype didn't have to be that way. The mother's genotype could have also been a Y plus with a W on one of the homologs and a Y with a W plus on the other. But in this case, this is the mother we're going to use. And in flies, they typically do this thing where it almost looks like a fraction, but it comes from the drawing out of the two chromosomes, and somewhere along the line in Drosophila genetics history, one of the lines stopped being drawn, but you're supposed to think of it as these are the two chromosomes for the homologous pair. So that's the mother's genotype. So she fits the criteria. She is double heterozygous. And then the father, he is completely recessive. Little y, little w. So his genotype, his arrangement is kind of not interesting. There's not more than one possibility for that one. So this is where the cross is done. So I'm just drawing out the mother's exact genotype here and the father's exact genotype, and they mate. Now, first, of course, in the mother's body, the gametes would be formed. In the father's body, the gametes would be formed. We know for the father, all the gametes would have a chromosome with a Y and with a W. But for the mother, when her body makes gametes, since these genes are linked, most of the gametes would have a chromosome with a Y plus W plus, or a chromosome with a YW, and only a smaller number would have the crossover types. And that's based on our concept, our rule that says parental allele combinations are more common in the gametes and therefore more common in the offspring than the crossover allele combinations. And so when you look at the offspring, you see that that is reflected in the offspring, all right? 493 offspring are yellow body with white eyes. So that offspring got this chromosome from the mother and this chromosome from the father. I guess it could be reversed. On the next one, 502 offspring have a gray body and red eyes. Now, you know that this one had to come from the father because he only has one type of chromosome allele combination in his sperm. And so this top one had to come from the mother. And so you see this chromosome combination and this combination here, those are the two parental from the mother. Now down here in much smaller numbers, you have a group that have only 3 that have a gray body with white eyes and only 2 that have a yellow body with red eyes. And again, this bottom chromosome is the one that came from the father. So we know that the top chromosome is the one that came from the mother, but it would only be able to come from the mother after a crossover event in meiosis. So lots of meioses happen without a crossover between gene Y and gene W, but a few there came from a crossover that a few of the gametes do have a chromosome that have the results of a crossover. And so when those gametes get fertilized, then you see these small